March we onward toward an AP exam. This is the second lesson of Unit 7 in Canandaigua's AP Calculus BC course. Want to take a look at limits of sequences. Want to take a look at limits of sequences, a little bit of review from our last lesson, and then a quick theorem that will help us out in a time of need. So, I want to play everybody's favorite game. Does it converge? And so I've got 4 sequences to consider. This is the sequence A sub n. This is the sequence B sub n. This is the sequence C sub n. And this is the sequence D sub n. And the question each time is, as n gets bigger and bigger and bigger, do the terms of that sequence approach one fixed number? To converge means as n gets bigger and bigger, the terms approach, that's terrible handwriting, approach some fixed number. Not 2 fixed numbers, not bouncing back and forth. The terms settle down. Get a wife, couple kids, stable job with possibility of advancement. That's what we're looking for. So, take a moment, hit the pause button, and think to yourself, do these sequences approach some fixed number? Think about it. Thinking. Thinking. Think. Okay, so I'm assuming that you hit the pause button. If you haven't, you're about to get the answers. Here's the way this goes. A sub n. What happens? The numerator, this part gets bigger and bigger and bigger and bigger and bigger. That has little effect. This gets bigger and bigger and bigger. So let's ignore this entirely and see what happens to that. Because that's the stuff that where the numerator is getting larger and larger and larger, the denominator is getting larger and larger and larger, and sure enough, A sub n approaches the number 2. And so the answer to that question is yes, that sequence converges. Well, let's take a look at B sub n. What did you say in the B sub n case? Well, in the B sub n case, this gets closer and closer to 1. This bounces back and forth. If you want to sound really smart at a math party, we call that oscillation. And so when you get to sufficiently large n's, you're basically dealing with a sequence that's 1, -1, 1, -1, 1, -1, 1, -1, and so on. So this sequence does not converge because it oscillates. Third, C sub n. As n gets larger and larger, the -1 and the +1 don't have much of an effect at all. So C sub n approaches 3/2, and that answer is yes. And then D sub n, let's see. This gets orange. This gets closer and closer to 3. This is an oscillation. 2 L's. So it's bouncing back and forth between 3, -3, 3, -3, and so on. This does not converge. By the fundamental law of textbook examples, there must be 2 that do and 2 that don't. Yay. But What about this? What about that? The numerator bounces back and forth between numbers that are close to -1 and numbers that are close to +1, and numbers that are close to 0, and numbers just bouncing around. The denominator is getting bigger and bigger and bigger and bigger and bigger and bigger. So the denominator is definitely growing. The numerator is never going to be bigger than 1, and the numerator is never going to be smaller than -1. And so I think we can say this converges, but to do that, we need a theorem. This is called the Sandwich Theorem. It is also sometimes called the Squeeze Theorem, depending on who writes the book. And it goes something like this. If the limit as n approaches infinity of some sequence a sub n is L, and that L is also the limit as n approaches infinity of some sequence c sub n, and there is an integer capital N such that a sub n is less than or equal to b sub n is less than or equal to c sub n for those sufficiently large n's, then the limit as n approaches infinity of b sub n is also L. We should talk about what that means in plain, simple English. If you can trap the sequence you're interested in between two other sequences whose limit is L, then the sequence that's trapped between them must also go to L. Let's talk about why that's true. We can prove it formally in some very advanced college course, but let's talk about informally why that's true. Well, what does it mean for the limit of a sub n to be L? It means that as n gets larger and larger and larger, the a sub n terms are getting closer and closer to L. At the same time, the limit of the c sub n's is L. So the c sub n's are getting closer and closer to L. Now the b sub n's are between the a sub n's and the c sub n's. They're not going below the a sub n's, so the limit won't be less than L. They're not going above the c sub n's, so the limit won't be greater than L. And if the limit isn't smaller than L and it's not bigger than L, it's got to be L. That's the way it goes. How does that help us here? Well, I'm going to use the Squeeze Theorem. It's called the Squeeze Theorem because the two sequences a sub n and c sub n squeeze b sub n toward L. Let's show that this converges. And I'm going to do that really easily. We know that the cosine of n is in between -1 and 1 for all n. For all n greater than or equal to 1, which is all that matters for the case of a sequence. Which means that the sequence that we want is trapped between -1 over n and 1 over n. Now, the limit as n approaches infinity of -1 over n, that's 0. And the limit as n approaches infinity of 1 over n, that's 0. Therefore, the limit as n approaches infinity of cosine n over n has to be 0. because the red sequence and the blue sequence trap our sequence, and their limits are the same, so those sequences squeeze our sequence to a limit of 0. Awesome. When you come to class tomorrow, I'm going to have 2 sequences for you. Those 2 sequences, we're going to play everybody's favorite game, Do They Converge? 2 sequences for you tomorrow. One is the sequence 1 over n factorial. The other is the sequence sine n squared over 2 to the n. Your job between now and tomorrow is to consider, can I trap those between 2 sequences that I know converge? Can I trap those between 2 sequences that I know converge? That's your question. We'll see you tomorrow.